Welcome to this first real video in my series on tensors. The previous two videos were mostly on giving motivation and background on tensors. In this video, we're going to get started doing some actual real math. So the first thing we're going to learn is forward and backward transformations. These are the rules that let us move back and forth between different coordinate systems. I mentioned in the previous videos that tensors are invariant under a coordinate system change, so understanding how to move back and forth between coordinate systems is going to be really important for understanding tensors. Okay, so let's start off with the forward transformation. So I have two-dimensional coordinate systems here, the old basis E1 and E2, and the new basis E1 tilde and E2 tilde. So remember from linear algebra that the word basis just means a set of vectors that give us the main coordinate directions for our space. So we have the old and new coordinate systems, or the old and new basis. So the forward transformation will move us from the old basis to the new basis. So how does that work? Well, all we need to do is to build the new basis vectors out of the old basis vectors. So let's start with E1 tilde here. How do we build E1 tilde out of E1 and E2? Well, it looks like we need two E1 vectors and one E2 vector. So I'll just write that in here. Now, what about E2 tilde? So it looks like we need half of E1, but it's in the opposite direction, so that's actually minus a half. And then we need a quarter of E2. So I'll just write those in. Alright, so what we've done is we've written the new basis vectors as linear combinations of the old basis vectors. And if I wanted to, I could store these four numbers in a 2x2 matrix called F for forward. And so that's really it. That's the entire forward transformation. If we know the matrix F, then we know everything we need to know to construct the new basis from the old basis. Okay, so what about backward transformations? As you'd expect, it's basically just the same thing but in reverse. So we build the old basis vectors using the new basis vectors. So how do we build E1 using E1 tilde and E2 tilde? It's a little more confusing this time, but it looks like we need a quarter of E1 tilde and exactly one of E2 tilde, but facing the opposite direction, so it's actually minus 1. So I'll just write those in. And what about E2? It looks like we need a half of E1 tilde and two E2 tildes. And again, we can store these four numbers in a 2x2 matrix called B for backward, and that's it. That's the backward transformation. So if we know the matrix B, we know everything we need to construct the old basis from the new basis. Now you might be thinking here, we have the matrix F and we have the matrix B. Are these really two different things? They kind of do the same job but in opposite directions, so are they really so different? Well, let's see what happens when we multiply them. So this might actually be a good exercise for you to review matrix multiplication. To multiply two matrices, we write them like this, and to get this entry of the resulting matrix, we take the dot product of this row vector and this column vector. So in this case, it's 2 times a quarter plus 1 times a half. So that's just a half plus a half, which equals 1. Alright, so I'm going to let you do the other three entries, but what you'll find is you get this matrix here with 1s along the diagonal and 0s everywhere else, and that is, of course, the identity matrix. So what this really means is that F and B are inverses, or another way of saying that is that B is equal to F inverse. So why am I using two different letters here? Why use F and B when I could use F and F inverse? Well, just visually, I personally find it easier to tell the difference between F and B than between F and F with a tiny little -1 up here. So even though B is equal to F inverse, I'm just going to keep writing B. Okay, so that was an example in 2 dimensions. What if we want to generalize this to n dimensions? Well, it's basically the same process. We have n old basis vectors, E1, E2, all the way to En, and we have n new basis vectors, E1 tilde, E2 tilde, all the way to En tilde. And we need to decide how to build the new basis vectors out of the old basis vectors. And we do that just by choosing the right coefficients so that all of these linear combinations work properly. And again, we can write all these coefficients in a matrix, This time it would be an n by n matrix instead of a 2 by 2 matrix. And so that's our matrix F. Now writing out all these equations is kind of annoying, so let's see if we can find a better way to write this. So if I wanted to build ei tilde vectors out of the ej vectors, what I would want to do is write ei tilde as sum of the ej vectors, but I still need to decide on the coefficients. So what would those be? Well, if you look up here, you'll see that F21 tells us how much of E1 makes up E2 tilde. Okay, so F21 tells us how much of E1 makes up E2 tilde. And over here, F1n tells us how much of En is inside E1 tilde. So really the coefficient I want here is Fij. Fij tells us how much of Ej makes up Ei tilde. So really this summation summarizes all of the above equations nice and simply. So this is the forward transformation in n dimensions. Now for the backward transformations, we can do the same thing. We just write out all the old basis vectors as linear combinations of the new basis vectors. We can write these coefficients in an n by n matrix called B. And we can summarize all these equations using a summation. Ei is equal to the sum of ej tildes with the coefficients being bij. So that's the backward transformation in n dimensions. Okay, so we have the forward and backward transformations. Can we prove once again that they are inverses? Well, I'll start with the backward transformation just here. And if you'll notice, the forward transformation gives us an equation for ej tilde. So I'm just going to substitute that in for ej tilde here, and we get this. And rearranging some of the summation signs, we get this. Okay, so let's just put this on a new slide here. So looking at the formula, what's going on here is that we're building the old basis vectors using a summation of the old basis vectors. And what we need to do is we need to decide what this middle part of the equation should be. So why don't you pause the video and take a few seconds to think about what this middle part should be if we want these equations to make sense. Okay, so what we really want at the end of the day is for E1 to equal E1, we want E2 to equal E2, and so on and so forth. We don't want any extra basis vectors in here being added because that wouldn't make any sense. So what we really want is for this middle part to be 1 when I is equal to k, and we want it to be 0 when I is not equal to k. Right? That makes sense? And really, if you think about this as a matrix, where I gives you the row and k gives you the column, putting 1 where I equals k means we have 1s where the row is equal to the column. So we get 1s along the diagonal line here, and then we would just get 0s everywhere else. So again, 1s along the diagonal, 0s everywhere else. Once again, we showed that multiplying f by b gives us the identity matrix, so f and b are inverses of each other. Now this behavior where we have 1 where I equals k and 0 where I doesn't equal k, this behavior ends up being so common that we give it its own symbol called the Kronecker delta. So whenever you see the Kronecker delta, just think of this relationship right here. It's a bit like telling you what the entries of the identity matrix are, where we have 1 where the row is equal to the column and 0 everywhere else. Okay, so to sum up what we learned in this video, we learned that formulas for the forward and backward transformations in n dimensions, and we also showed that the forward and backward transformations are inverses of each other, because when we multiply the f and b matrices, we get the identity matrix whose entries are given by the Kronecker delta symbol here.